So I'm here today to present the paper, A Digital Twin Framework for Improving Energy Efficiency and Occupant Comfort in Public and Commercial Buildings. And my name is Anders Clausen. I'm an assistant professor with the University of Southern Denmark. So I'll start out with a brief background and motivation for the work that we have done in this paper, and then I'll go into explaining the approach that we have taken. I'll then present our experiments and go on with a discussion and conclusion. So buildings today, at least in our part of the world, account for approximately 40% of the total energy consumption. And this means that energy efficiency, of course, is very important in the context of buildings. To this end, we've seen a lot of deployments of building intelligence solutions that addresses issues concerned with plugged-in devices and building instrumentation. This sort of instrumentation has helped us achieve more effective building automation, where we can control the environment of buildings. And while doing so in an energy efficient manner, we can also ensure that we actually have occupant comfort, which is, of course, crucial in this type of building. Now, I'm going to introduce to you the case building that we've been worked with in relation to this paper, and actually it's the same building as Hamid mentioned in the previous presentation. It's building OU44 at University of Southern Denmark, Campus Odense. This building is rather advanced. It has sophisticated instrumentation across all the rooms. It's a teaching building used for teaching curriculum to students at the university, and it's also used as an office building. It has a comparatively high level of comfort, where the air quality and the temperature is controlled by building automation, and it's done so in an energy efficient manner. And the building itself is very energy efficient as well, with high levels of insulation. This may not pose the best case if you present it like that, because of course this is already a very advanced building, and it's already a very efficient building if we compare it to traditional buildings or older buildings, but it's still not optimal. The building automation strategy is reactive, which means that it'll react to changes in the state of the building. But of course, this comes with a couple of drawbacks. The building dynamics are slow, which means that if some comfort parameter is violated, it'll take some time for the building automation system to correct this, because the building dynamics will ensure that this goes on for a while until we are back in a comfort state that we would like to be in. The reactive control is also completely agnostic with respect to the planned use of the rooms in the building. So it cannot take into account when the building is going to be used or when rooms in the building are going to be used, and it has to prepare for some scenarios that might occur. This also means that it cannot plan for the utilization of energy. And so what that means is that even though we have solar panels or photovoltaic panels installed on top of the roof of the building automation system cannot take into account when the production is high, because it is merely reactive, as I mentioned. So it has some fixed set of rules that it has to follow, and it cannot take into account any sort of dynamic events other than the ones that it can measure when the building state changes. Now, to address some of these issues, we are proposing a digital twin framework for model predictive control based building automation. And so once we go into the domain of model predictive control, of course, we can take into account planned things into the future, because that is how model predictive control works. We can predict what's going to happen and control based on the predictions that we make. I've provided here on the screen a quick overview of the digital twin framework that we're proposing. And I just want to be sure, can you see my mouse when I move it around here? Or is the mouse not visible?
That's a yes.
That's a yes, all right. So as you can see, I've divided the overview here into sort of 3 different layers. And I'll actually start with the middle layer, which is where we have SMAP and the archiver. Essentially, what this is an implementation of a common data format pattern, where we have this REST-based middle layer that enables us to seamlessly communicate between different software components that might be very different in how they're constructed and in the data formats that they're using internally. But this middle layer helps in proposing a common data format across all applications that are going to talk to each other through this SMAP layer. And so it enables us to deploy and remove, for that sake, components in the architecture as we see fit, as long as, of course, as we adhere to the common data format. Now, at the green layer at the bottom here, we have interfacing towards instrumentation in general and towards external systems. So if we look down here, we can see that we have some Sovis cameras drivers. These are drivers that interface towards specific instrumentation that have been deployed in order to adhere to the needs of the Occur prediction algorithm. I'll get back to that in a bit. We also have some representation of both a physical and a virtual building. So the physical building is, of course, the building OU44 that I described before. And this is represented through a set of drivers that interface towards the physical hardware installed in the building. And this is again represented in SMAP, so that the data format is again common. And we actually did that for a digital building as well. So the digital building is nothing but a simulation, but it is exposed in the same way as the physical building towards SMAP, which means that when you perceive either a simulation or real building through the SMAP layer, they will appear identical. This also means that it enables us to very seamlessly transition between simulation and practical application of our zone control application up here, because all that we have to do is change the configuration to write to points that are either in the digital building or in the physical building. Now, I'm going to say that the experiments that I'm going to present today are experiments conducted on the physical building. We have a previous paper where we demonstrated the ability to do the same thing on a simulated building. So I can refer you to the paper that we've written and submitted to this conference, where we actually have a reference to that paper as well. We also have a weather driver here that interfaces towards a local weather station, which gives us a pretty accurate idea of what is the current weather in the area where the building is positioned. Now at the top here, we have our applications, and there are two applications in the current digital twin framework. Occur is an application used to predict occupants and occupation of different zones in the building. And the zone control application is the application that we use in order to do the actual model predictive control. I'll go a bit into both of these applications in the following slides. Now, starting out with Occur, this is an occupancy prediction and estimation algorithm. So it has a reasoning engine that it uses to create an estimation of the current number of occupants in the room, and a prediction engine as well, where it can predict its forecast on the future utilization of a given zone. The Occur algorithm has two ways of achieving these results. So you may opt to either use a camera-based approach or an approach based on existing building instrumentation in peer sensors and CO2 sensors. Now, the peer sensors and CO2 sensors in a building like the one that I just described are inherently there. They're used to aid in the default operation strategy in order for the building management system to take into account state changes in air quality and in occupation of the rooms. This means that this has the advantage that, of course, this system instrumentation is already there, and you don't have an extra cost or extra complexity added needing to install additional hardware in the building. It has some drawbacks, though, compared to the solution that uses dedicated cameras for estimating and predicting occupants, and that is that it's inaccurate. It's inherently inaccurate compared to the cameras, because it is subject to a lot of other noise sources that is otherwise not relevant when we are looking at the cameras. On the other hand, though, the cameras are expensive to install, and they are expensive to buy, and of course they need to be maintained, and they have a very specific purpose, namely estimating the current number of occupants in a room. So while they are more accurate than the peer plus CO2 based sensor solution, they are also more expensive, and they have a few other caveats as well, as we found that they were also subject to faulting actually pretty often, and that's of course unfortunate. And the results of such a sense of faulting is actually something that we also see represented in our result, and I'll get back to that a bit later. So the way that this works is that Occur will draw the data that it needs from the SMAP layer, and this data, of course, is either data from the SOBIS camera driver or from the PEER plus CO2 sensors. In our paper here, we use the camera data, which is cameras were already installed in the room in that we were doing on our experiments on. And so, of course, this was an ideal approach for us to take given the proposed accuracy of this type of sensor. Once the Occur algorithm has created its estimation and prediction of future occupants in the zone, these are written back to SMAP, which means that this is again available across the suite of components that are interfaced towards SMAP. And of course, this is also where we draw the data from in the zone control application. So as for the zone control application, our zone control application is based on a genetic algorithm framework called Controlium, and it also makes use of a generic zone model. Now, the Controlium framework enables us to define optimization variables and objectives as objects in object-oriented programming, which provides us with a first-order abstraction of these somewhat complicated entities. It also enables us to define configurable archetypes because, as you would know from object-oriented programming, we can parameterize stuff and we can draw out variables in external configuration files that enables us to create a configuration for a specific experiment and use that without having to reprogram the application itself. In the digital twin framework zone control application, we have two types of optimization variables. We have one set of optimization variables for the VAV damper position. This is because we are able to control the position of the VAV damper position in the building that we've been using. And we are also able to set a temperature set point. So since these are the entities that we are able to control, these are the entities that we would like to find an optimal solution for so that we are able to operate them energy efficiently and to ensure occupant comfort. Now, in order to ensure that these are actually the values that we achieve, the optimal values that we achieve, we have defined 5 different types of objectives in our zone control application. We have one CO2 comfort objective, which is concerned with ensuring that the threshold for CO2 or comfort level of CO2 is not violated. We have a lower and upper comfort temperature objective, which ensures that the temperature, or strives to ensure, as we shall see, that the temperature is neither too low or too high. And we also have a ventilation and heating conservation objective. So of course, what we want to do in an energy efficient setting is to ensure that we are not ventilating more than needed and we are not heating more than needed. Now, an important point here is that we do not have air conditioning in this building, and this is actually common throughout the buildings that you see in Denmark. So we do not have air conditioning that we can use to suppress high temperatures, and we will see the consequence of that later as well. This also means that while we will strive towards staying within a temperature bound, there's actually little we can do once the temperature starts to rise above the upper comfort temperature threshold. For each of the objectives that I just talked about, we have an evaluation function. And this function is a function which is used to evaluate the suggested values for the VAV damper position and for the temperature set point. They can optionally choose to make use of a generic zone model, which will calculate the consequences of a particular setting for VAV damper position or a temperature set point and calculate the resulting state of the building. I'll come back to that in the next slide that we should see. They're implemented as minimization function, which means that we strive to have a value of 0 from each objective. And the values returned by these evaluation functions are used by the genetic algorithm to generate a population of solutions. Which solutions goes into this population is determined based on the Pareto criteria, which I will not go into here, but which is elaborated in the paper. The final solution from the population, once we're done with running our optimization algorithm is selected based on social metrics. And again, here I'll refer back to the paper in order to not get too technical. But the point is that once we have a final population, of course, we need to select one solution from the set of possible solutions in order to actually do something to the physical building. Now, for the CO2 temperature and heat conservation objectives, we actually make use of the generic zone model. And so, as I mentioned, the zone model will calculate the consequences of actuation. This means that once you impose a set of set points for the ventilation system and for the heating elements, the thermostats in the building, you have a physical consequence. The generic zone model will give us an estimate of what will these consequences be. It's built as a gray box model, which means that it's incomplete, but we actually use or make exploit of that feature in our framework, in that we can calibrate the zone model towards a specific zone if we want to use the which means that we can use the zone model across different zones, provided that we will use data from that particular zone to calibrate the zone model. It considers solar gains, conductive and convective heat loss. It considers infiltration, occupancy, heat, and CO2 gains. It also considers heat gains, of course, from the radiators, and it considers whatever the dynamics induced by the ventilation system is, which might be both suppressing the temperature and also, of course, improving or removing CO2 out of the zone. Now try to visualize the flow that goes on with our evaluation of a particular solution here. So to the left, we see that we have the genetic algorithm. It generates a solution. This solution constitutes a set of set points for the CO2 and a set of set points for the temperature in the building. This is fed into the configured zone model. So when it's configured, it means that it is calibrated towards a specific zone, along with measurements for the solar radiation, the outdoor temperature, occupancy, and the temperature of the ventilation airflow. This enables it to calculate, for instance, and this is just an example, the resulting CO2 in the zone, which now considers both the occupants and the current state of the zone. And this resulting CO2 state is fed into the CO2 comfort objective, which will use this value and hold it against a threshold for CO2 to calculate how satisfied am I with the solution generated down here. The evaluation is fed back into the genetic algorithm, and this goes into determining whether this solution should belong to the current population of best solutions or not, based on the Pareto criteria, as I mentioned. Now to the experiments. We did our experiments at the U182 room in building OU44 at the University of Southern Denmark. This is the room that you see here to the right. The purpose of the experiment was to do a proof of concept that we could actually substitute the current building management system strategy with the strategy implemented by a zone control application and the digital twin framework as a whole. So we wanted to be able to plan energy consumption based on occupancy, weather, and the current state of the building. And we wanted to maintain comfort levels which are comparable to what we are achieving with the existing building management system. So the methodology that we used was that we measured the baseline CO2 and temperature during default control mode across a day. And we then replaced the existing control strategy with the digital twin framework, did measurements across a day where the digital twin framework was in charge of controlling the room. And this, of course, enables us to compare the results of the two approaches and see at least if this seems like a viable solution. Now for the baseline experiment, where we had the default operation with the building management system, we had some settings configured in the building management system. This is not settings that we have controlled. These are the settings that are there from the technical department. They have they're running with a 21 degrees fixed temperature set point. They have 3 levels of actuation for the VAV damper. When the CO2 level is less than 750 parts per million, the VAV damper is 45% open. When it's between 750 and 900 ppm, the VAV damper is 70% open, and when it's greater than 900 ppm of CO2 in the air, the VAV will be fully open. We observed the baseline on October 24th, 2018, and we see that largely the existing approach is able to maintain the air quality below the CO2 threshold, which means that we have below 1000 ppm, which is what we desire. We also see that throughout the day, the temperature comfort range is somewhat violated. If we look over here, we can see that I marked the desired upper level of temperature at 22 degrees, but we see that most of the day we actually exceed that. This is back to the case that I mentioned before, that we don't have an opportunity to actively cool the buildings in Denmark, aside from using the ventilation system, which is not very effective at all. Now for the experiment with the digital twin framework, we also had some settings. So these settings are configurable. We can configure them depending on where in the world we are applying it and in what industry we are applying it. So we've configured the optimization variables with values between 0 and 100 with a 10% resolution, which means that we have 10 possible values for the VAV. We are planning for 7 hours ahead. This includes the current hour. We also have a temperature set point, which can be between 20 and 30 degrees with 1 degree resolution. We have fixed a 900 ppm CO2 objective limit for the CO2 values, which means that it'll strive to maintain the CO2, the calculated resulting CO2 levels below 900 ppm. This is to account for inaccuracies in the generic zone model. And we are striving to stay within the window of 20 and 23 degrees lower and upper comfort temperature limits. We have conducted the experiment on December 14th, 2018, and we see that from the results that the CO2 levels are largely kept, again, within the desired range. We only have a small violation here around 1430. We also see a kind of peculiar pattern in the results here, in that the VAV damper position seems somewhat reactive, which is actually what we are trying to avoid with this approach. The reason for this is that we figured after the experiment had run that we actually got somewhat inaccurate estimates and predictions from the sensors installed in the building, and it turned out that one of the camera sensors was actually faulty. So luckily, the digital twin framework also takes into account the current state with respect to CO2 and temperature. So it is able to react to the state changes, and even though we don't have an accurate estimate of the amount of people in the room, we are able to actuate the VAV damper to actually suppress the CO2 levels. With respect to the temperature, we can see that in this case, we stay more within the boundaries of the desired temperature limits. As we can see here between 1130 and 1230, that it tries to counter a dip in temperature because it perceives that if it doesn't do anything, the temperature might drop below the desired temperature or the lower threshold of temperature. And of course, this is also a consequence of us being later in the year. And this gives us an unfair advantage with the experiment as opposed to the baseline measurements with respect to keeping the temperatures lower, because now, of course, the temperature outside is colder as well. Now for the discussion and conclusion, we see with the baseline measurements that the CO2 is mostly kept within threshold, and ventilation also happens when we don't have occupants in the room, because ventilation actually runs throughout the day at, as I mentioned, a minimum of 45%. We also see that the upper temperature limit is exceeded most of the day, and we cannot directly blame the strategy for this because we simply don't have effective actuations to do once the temperature is exceeded, the temperature limit is exceeded, since the building is not equipped with an air conditioning system. From the experiments, we see that we maintain comfort levels with respect to CO2, which is largely comparable to that of the baseline experiment. We also see that the VAV damper position is now operated in its full range between 0% and 100%. And when there are no need for ventilation in the room and no planned need for the ventilation in the room, we see that it actually goes to a full 0% at some times, which of course tells us that now we are able to shut off ventilation also during operational hours without doing any further violation of the CO2 threshold. CO2, the temperature limit is hovering around, or the temperature is hovering around the temperature limit. And again, it's hard to directly compare. We are in a different time of the year. And again, we don't have measures to suppress the temperature once it gets too high. But our immediate observation tells us that it's no worse than what we see in the baseline experiment, at least. And so for the conclusion, it seems that we are achieving comfort which is largely similar to that of default operation. We have the potential to achieve idle ventilation when no ventilation is needed. Of course, this would be improved if we have accurate predictions of occupants. And we also see some prospects in this, namely that we can increase energy efficiency. Of course, back to again that we can now plan for use of the zone, and we can plan our energy consumption to take into account local production if that is what we needed, by adding additional objectives in our optimization problem. So that's it for me. Thank you.